Hello, in this video I would like to do a short review on Calculus 2. We will do both theoretical and practical review. Firstly, let's talk about topics we cover in this course. Okay, so the first topic is integration. We study integration by substitution and integration by part. Okay, so what is substitution? Let's say this: when you see a composite function, right, means f g of x like this, and integral, and then maybe something like g prime dx. Basically, you need to do substitution u equal to g of x. So that is substitution. You would recognize that, actually substitution is some kind of inverse of the chain rule, right? Of the chain rule. Let me remind the chain rule in here because, anyway, we need the chain rule in the future. So the chain rule says if you differentiate f and then g of x in here, you have to differentiate the outside function, which is f prime evaluated at the inside, then multiply with the derivative of the inside. So that is the chain rule. Okay? The most difficult in this topic is trig substitution. Okay? Trig substitution. We know three forms of this. The first form is u a squared plus u squared. The second form is a squared minus u squared. And the third form is u squared minus a squared. So for this form, you would use u equal to tangent of theta. And for this guy, you use u equal to sine of theta or cosine of theta. For this guy, you would use u equal to secant of theta. I just remind you this. Anyway, you need to have a formula sheet, right? And then on the test or final exam, you can use those formula sheets. And one more thing I want to mention is we have a lot of formulas in this topic. So I don't require, and it's not necessary to memorize all of them, right? We just need to know how to find them very fast. That's it. Okay. One more thing I want to mention in this topic is, sometimes if they give you a polynomial, right? Let's consider a simplest case, that is quadratic polynomial, like a x squared plus bx plus c. You have to know how to rewrite this polynomial in the form of this guy or this guy or this guy. Okay, that is very important because if you have this polynomial and sometimes you cannot integrate directly, you have to convert this into one of those forms and then use trig substitution. I want to remind you one formula of this kind of problems. So we have a plus minus b square equal to a square plus minus 2ab plus b square. So basically, you need to use this formula, right, to convert this guy into one of these, okay, into one of these. We'll consider that, in more detail in the second part of this video. Okay, that is about trig substitution. About substitution, let's talk about integration by part. So integration by part, there's some kind of inverse of the product rule. The product rule says you have product of u and v, and you differentiate that, you get u prime v plus v uv prime, right? And the integral is integral of u prime u dv equal to uv minus integral of v du. Basically this formula is a consequence, is direct consequence of of the product rule. You see that if you integrate both sides of the first identity, you get the second one. So the most important in this is, you have to recognize, if they give you an integral, you have to see, u and then dv. Once you have u and dv, you need to differentiate right away. You get du, something like dx in here, and then dv, you saw v equal to integral of something. And then, if you don't remember the formula here, so you may think like this. So once you have u in here and then v in here, you multiply, your original integral. I will say this, your original integral u dv equal to, uv, right? You see, it's like just take product of u and v, and then you subtract what you get in here, right? With this guy, you subtract. Don't forget about that, minus v du. Okay, that is about integration by part. All right, now let's talk about application of integrations. The first problem in this is area problem. It's the area problem. So if they give you two functions, right, f and g, and let's say we consider some interval a and b. A and b could be, common zeros of f and g. Okay, so look like this. This is f, this is g, and here is a, and here is b. So they ask you to find the area of the region enclosed by curves of f and g. So the area is equal to integral from a to b, f of x minus g of x dx. I write, absolute of f minus g in general form because sometimes if they just give you f and g, you don't know which function is bigger than another. So you write absolute. And each time when you solve the area problem like this, you have to make sure about the graph of f and g. So otherwise, you cannot remove, the absolute in here, and then you cannot integrate. Okay? I just remind you this problem, right? I don't want, to make the situation more complicated. But, sometimes you have something like this, right? And in one interval, f is bigger than g, but in another interval, g is bigger than f. So sometimes you have to split your integral, right? This integral into two integrals. If the intersection here is c, so basically you have to consider interval from a to c and from c to b, and then you have to take the absolute. You have just, take the absolute of two integrals and you get the total area of the region enclosed by function f and g. This is what we learned in Calculus 1, right? The next problem in here. Okay, now let's talk about picture first, right? And then I'll point out problems we need to learn. So you have a function. So basically you have some curve right here, right? Let's say on interval a and b. This is function f of x. We know how to find the area of the region. That's what we just talked about, right? The area of that region. So that is the first problem. Now, if we rotate this curve about the x-axis, right? So you get some solid region. And for this solid region, we are interested in some problems like first, we need to find the volume, right? We need to find the volume of solid region. So you see, and then, we need to find the surface area, right? The surface area of this solid region. And about the curve, we still sometimes need to find the arc length, okay? The arc length. So you see, this is 4 problems related to a curve. The first one is the area problem. The second one is the volume of a solid region. Solid, I think I have table in here. The third one is surface area of that solid region, and the last one is the arc length of that curve on some interval. Okay? So let's talk about volume of solid region. For the volume of solid region, we study two methods, the disk methods and the shell methods. So what does mean the disk methods, right? When you rotate your curve about the x-axis, okay, let me make another curve, or maybe just consider this picture, right? So you want to find the solid of this region. Basically, I have to, split. I have to split, my solid region in sub-solid region. Okay, you see this? And then we approximate the volume of each disk, the volume of this disk, right, by the volume of, a cylinder like this, or, guy of disk, right? And then since we have several, sub-regions in here, so we sum them up, we get a Riemann sum. You see that? We get a Riemann sum, and then, we consider a limit process. We do a limit process, and we get the exact volume. And so what is the formula of the disk method? The disk method say you have, this guy. So basically that is, I would say, here is this function f of x, right? If you have some x in here, x right here, you have some x right here, so here you should have f of x. So the volume of this disk, what is the volume of this disk? So the volume of this disk is equal to, the height, right? The height, which is delta x, and then, the area of the base. The area of the base look like this. So the area of the base is the circle. So the area of the base is just pi radius square. So by the disk method, the volume is equal to, I will write here, integral from a to b, okay? So I write the height is dx, which is delta x, and then pi, and then I have f of x, which is the radius, and then square. You see, that is the volume of our solid region using the disk method. And mention that when you rotate some curve about the x-axis, right, you get some solid region, and the volume of that solid region looks like this. So that is the main thing, right? You rotate about the x-axis, you use the disk method, okay? So now let's talk about the shell methods. So for the shell methods, let's make another picture, right? Let's make another picture right here. So I have that picture in here, okay? So my region looks like this, and then I rotate about the y-axis. If I rotate about the y-axis, I get the following picture. Now, let's say they're symmetric, right? So I get something like this, okay? So my region looks like this. My solid region looks like this. You see, in order to find the volume of this guy, we, sometimes we cannot use the disk method. And most of the time, we cannot use the disk method. We need to use the shell method. Okay, how does the shell method work? Okay, let's say I will ignore this part because this part is well known, right? So if this is from A to P, this guy is just, a cylinder. So I don't talk about this, okay? I just talk about this guy, rotate about this guy. Don't forget that. Because, we just rotate our region right here. So I think I make an extra, it's not something correct, right, in here. Let me erase this. So we still have the y-axis in here. So our solid region looks like this, okay? So how to find the volume of this guy? Okay, in order to find the volume of this guy, I will divide AB into intervals, right? And I have something like this. I have some this like this, okay? But when you rotate this guy about the y-axis, so you get some disk. Your disk look like this, right? This look like this. Don't forget that, And then, once you have that, right, you have to, again, just divide and then, approximate and then sum them up, you get your integral, okay? So basically, if this is x, I'm talking about rotating about the y-axis, right? So if that is the x, so I need to find the volume of each shell, right? Let's say shell like this, right? So the volume looks like equal to integral from a to b, because you divide from a to b, right? And then you need to find, the circumference of this circle, right? You need to find circumference of this circle. So what is circumference of this guy? That is equal to r times pi, right? But what is r in this case? This is a very special case. R is equal to just, x, right? R is equal to x. So I write that is pi right here, and then x. And then what is the height of this guy? This is the height. The height is just equal to f of x, right? This guy just equal to f of x. So pi f of x dx. So that is, two formulas for the disk and the shell method. I repeat again, right? If you change the axis of rotation, so the guy right here would be changed, right? Because, when you rotate about the y-axis in here, the radius is just x, right? And that is equal to r, the radius. So that's why you have r, pi, which is circumference, right, of the circle. And then f of x is the height. So, I want to tell about this in detail because that is the main idea, right? The main idea of integration. Anyway, you just need to apply the formulas, right? So please have a formula sheet with you. All right. So, we can use the same idea to find formulas of the surface area and then the arc length, right? Okay, let's talk about that. The surface area. So for the surface area, let me just remind you the formula, okay? For surface area. So I have the surface area just equal to, I hope that I remember that formula, but in case if I do wrong, right, I will do a correction. So for the surface area, I think I will have integral from a to b first, and then I will have the length, that is 1 plus f derivative of x square dx, and then I need to multiply with the f of x in here, okay? And then the arc length, actually I have to remind you the formula about the arc length first. So that is integral from a to b, square root of 1 plus f derivative of x square in here dx. And if you compare, right, this formula and this formula, you see there is some component of arc length in the surface area, okay? All right, so I think we have some formulas, right, of 4 problems related to a curve. This is about integration. Another part, which is brand new for most of you, is improper integral. So, what is that? Basically we consider integral from a to b, right? F of x dx. And your integrand function f of x is, let's say, continuous on a and b, right? So everything is good because the function is continuous at any point on a and b. But what happens if your function is not continuous at some point on this interval? Like integral from 0 to 1 dx over x to p, or integral from 1 to infinity dx over x to p. You see, when p is bigger than 0, 1 over x to p is not defined as 0. So that is improper integral, right? when p is bigger than 0, infinity is an improper integral. So in such situation, we need to consider limits, right? Uh, let's say integral from a to b, a to infinity, let's say that, a to infinity, right? A to infinity, f of x dx is equal to the limit of integral from a to b, f of x dx, and then b approaches infinity. This is, kind of definition, right? When your function is not defined at infinity, and when, infinity is the only improper point. So you have to evaluate definite integral, and then you tend b to infinity. So if this limit exists and equal to a finite number, right? So your integral is said to be converging. If this limit, does not exist, or equal to infinity, so your integral is said to be diverging, right? So we have to consider convergence or divergence of an improper integral. And this is two main integrals, right? In this course, we try to reduce any improper integrals into one of them. Okay, and let me remind you, for the first integral, for the first guy right here. Okay, so this integral converges if p less than 1. If p less than 1, converge. When p greater than or equal to 1, diverge. But for the second guy right here, okay, this integral converges when p greater than 1. When p less than or equal to 1, diverge. Okay, so be aware about that. I think improper integrals just close the topic, integration and application of integrations. Okay, that is the huge part in calculus 2. But that is not all. Let's move to the next part of calculus 2. The next part of calculus 2 is series. So you write something like this: infinite sum when n runs from 0 or 1, or from some finite number to infinity. Okay, so it means, you just consider sum of numbers, and of course this sum may be finite, this sum may be infinite. When this sum is finite, you say that this series converges. When the sum is infinite, you say that the series diverges. So our problem in this topic is to determine if a series converges or diverges. Okay, let me remind you some criterions, right? Some tests we learn and some basic techniques we use in this topic. Two main series, right? Two main series is the geometric series is sum and from 0 to infinity of a to the n, right? Another guy is harmonic series. Is sum 1 over n to p and from 1 to infinity. Okay, geometric series is important because we will use this to study power series. When absolute of a bigger than 1, the series diverges. So if the series diverges means, just equal to infinity, right? Let's say that. So it's nothing to say. But when, a absolute less than 1, or this is bigger than 1, or bigger than or equal to 1, right? If absolute is less than 1, this series converge, and we can find the sum of this series. That sum is just equal to, I'll write here, 1 over 1 minus a. Okay, it's just 1 over 1 minus a. So this is quite important, I'm writing here. Let's mention this guy equal to this guy when absolute of a less than 1. Okay, don't forget about that. About harmonic series, right? If you pay attention on integrals, you can see like this. These two integrals, right? Improper integrals we're learning here. So harmonic series look like those integrals, right? Basically, they have very tight connection. This harmonic series converge if p for p greater than 1, right? And diverge for p less than or equal to 1. All right, so like improper integrals, we need to to reduce. We need to reduce some most of series into geometric series and then harmonic series. I'm talking about this course only, right? So let's talk about some techniques that help us to make that. The first technique I would like to mention is similarity at 0, at infinity, similarity at infinity. So what does it mean? If they give you some polynomials, right? Like, here's a good example, n squared plus n, let's say square root, right? It's similar to, square root of n squared, and then it's just n. So what does it mean? That means, if they give you a polynomial, you just pick terms with highest degree. Because, at infinity, n squared is very fast, approaches infinity faster than, n. So that's why behavior of this guy is just is almost the same with the behavior of this guy. So this way we say they are similar. Okay. Another important one is, comparison. Again, comparison at infinity, right? Let's say that at that infinity. So we compare 4 functions. The first one is ln of n. You can apply any power m in here, right? We say that this function is very small if you compare with any polynomial n to, let's say, k, right? Where k, I write here, k is greater than 0, okay? Let's pick m greater than 0. And polynomial is very slow if you compare with exponential, like any a to the n. Like very typical one is, e to the n, right? And, for any a greater than 1, don't forget about that. Because when a less than 1, you have another exponential function, which is decreasing, right? And exponential function, is very slow if you compare with n factorial. What's that? N factorial, that is, 1, 2, and so on, and n. Just product of the first n natural numbers. So we use this comparison, to consider if a series converges, diverges. Okay, we'll discuss more about that. But anyway, I can give you some, some typical form of this. Like, you have series of ln of n squared over, let's say, over n, like this, right? And you say, yeah, this series diverge or converge. This series diverge, right? Actually, this is not a really good example, but anyway, this series diverge, right? Series diverge because, you can compare this guy with, 1 over n, right? Another one, you can do like series of n squared over e to the n, right? n from 1 to infinity. And saying this series converges. Why? Because n squared is very small if you compare with e to the n, right? So this series can be compared, right, with, I would say, should be less than or equal to sum of 1 over n squared, n from 1 to infinity. Because we compare e to the n with n to the 4. So that is very good example about how to use comparison at infinity, right, of those guys. I will tell you this, using this technique, we can avoid using L'Hopital rule, right? Using L'Hopital rule. But that's okay, we accept this in this course. So these two things helps us a lot, I will tell you this, because we can reduce some given series into one of them, into one of harmonic or geometric series, okay? Like this, if we use similarity, I want to give one more example about similarity, right? So say this series, I look complicated one, let's say 1 over 2 and then 3n plus let's say any number like 2 and then to the n, right? This series look horrible, right? But if you use similarity at infinity, you say, yeah, this guy is similar to what? Series from 1 to infinity, and then on the top you just pick n, in the bottom you pick 3n, and here to the n, right? And then this guy is just 1 over 3 to the n. And we know that this is geometric series, right? This geometric series right here. You see? This guy is right here. So since a is equal to 1/3, less than 1, the series converges. That is typical example when we can apply similarity at infinity and comparison to reduce our series into one of geometric or harmonic series. Okay? But at the same time, we still have different tests. Let me remind you about that. The first one is p-test. P-test is what we learn, right? We use similarity, right? And use harmonic series. The second one is integral test. For integral test, I would say it's hard to apply this, right? It's hard to apply this. But, in this course, I try to use similarity and comparison, right? So sometimes we just try to avoid integral test. But as I mentioned previously, right, about this integral and the harmonic series. So basically, we go from a series to integrals, right, to consider that. Because each, if you have an in here, and from 0 to infinity, an is your general term, right? And for each general term, you may find some corresponding function f of x. Just replace n in an by the x, so you get some function like that. And then if your an is decreasing, right? Decreasing, and not only decreasing to 0. So your series and then your integral from 1 to infinity, f of x dx, converge or diverge together. So that's about integral test. But I would tell you this, when we study improper integral, we still need to use similarity and comparison at infinity. So basically, if you understand these two things, so you don't have to go from series to integral. Okay? Next test, I would say that is ratio test. This is quite important because we use ratio test for power series. So ratio test says, yeah, if the limit of an plus 1 over an and go to infinity, if this limit is less than 1, the series converge, if this guy, saying here greater than 1, diverge, and if this guy equal to 1, sorry that we don't have any information, means no decision. We cannot do decision in this situation, okay? And another important one is right here, a root test. Root test. So instead of considering ratio, we consider root test. We consider n root of absolute of an and approach infinity. And again, for this guy, all these things just make a copy, right? So if this limit less than 1, converge, greater than 1, diverge, equal to 1, no decision. So that is about root test. Okay, I think that is all about numerical series, right? Numerical series. So I hope that this picture is good enough. Okay, now let's move to functional series. When absolute of x less than 1, the series x to the n and from 0 to infinity equal to 1 over 1 minus x. Okay, if you look at this formula in another order, all right, 1 over 1 minus x equal to series x to the n and from 0 to infinity. So you would think that actually the formula right here is representation of the function 1 over 1 minus x as a power series. You see that? For functional series, that is very important. We need to express some differential functions in a power series, because with the power series we can integrate, we can differentiate, and it is easier to approximate the function. So that is the main idea of the power series. Okay, let me remind you about general formula of the power series. So we learn the Taylor series, right? We learn Taylor series. That is an x minus c to the n and from 0 to infinity, where c is the center, c is the center of the series, and then an is coefficient, right? It turns out that if you have some differentiable function, right, your function can be represented in the form of an x minus c to the n and from 0 to infinity. And not only that, where an is equal to derivative of the other n at c over n factorial. Okay, so what does it mean? That means your function can be rewritten in the form series from 0 to infinity f to the n c over n factorial x minus c to the n, or that is f of c. When n is equal to 0, it's just f of c, right? When n is equal to 1, you have derivative sc over 1 factorial, and then second derivative sc at 2 factorial plus, I think I mixed the term in here. It should be this guy times x minus c plus second derivative c over 2 factorial x minus c squared plus so on, plus derivative of the other n c over n factorial x minus c to the n plus so on. You see, if your function is complicated, right? But if you can find derivatives, that's fine. You can express your function as a power series, and this is called Taylor series. This series is called the Taylor one, the Taylor series. Okay. So this Taylor series and centered at C. Don't forget that. What does it mean? That means when you change the center, right? When you change the center, C, you might have different changing C, we get, different power series. Okay, don't forget that. And then, what can we do with this formula? We can approximate the function. Like, since you have infinite, series in here, right? And, if you cut this series from some n, right? So I can write just f of x is approximately equal to n from 0 to n. Fn c n factorial x minus c to the n. So basically, you cut that and then you approximate your function by this part. And again, right, this is just polynomial, right? And once you have polynomial, it's always easy to work with them. That's it. And if c is equal to 0, so this series is called Maclaurin. It's just very special case of this. When c is equal to 0, so you have Maclaurin. Okay, so this is general theory about Taylor series, okay, and power series. Let me remind you the most important problem in this topic, and then we finish the review, okay? So the most important problem in here is find the interval of conversion. We may express a function, right? Function f in power series, but that does not mean this formula is correct for any x. Don't forget that. I'll write here, right? Not for every x. Not correct for every x. So what does it mean? That means we have to find the interval of x where the formula is correct, right? So that is about find the interval of convergence of that series. Okay, so let's consider general series like an x minus c to the n, and from 0 to infinity. In order to find the interval of conversion, we need to have, we need to do some steps. The first step, we need to use ratio or root test. So what does it mean? You have to consider a limit of, the whole an plus 1 x minus c to the n plus 1 over an x minus c to the n. Okay, and then n approaches infinity. Or that is about ratio test. Oh, let me write in here, right? That is, absolute of x minus c, limit of absolute of a plus 1 over an. If you use ratio test, okay? Or if you use root test, so you have to consider the limit of n root of, absolute of an, and then x minus c to the n, and go to infinity. So what is that? That is, again, x minus c, limit of n root of, absolute of n approaches infinity. All right. So it really depends on, on your series, right? It really depends on your series in here. So you have to decide ratio or root test, right? Why we call that ratio and root test? Because, we have this component in here and this component in here. You see that? And the absolute of x minus c is common already. So after this step, you need to set one of this value less than 1. Less than 1. Because we know that, the power series converge, right? When the absolute of everything is less than 1, you see it. Let me remind you about the geometric series, right? This geometric series. This says, this converges. That means, the identity happens if and only if absolute of x less than 1. So we want to have this power series, right? Correct. That means, the whole thing in here this limit and this limit should be less than 1. Okay, once you solve that, because this guy should be a concurrent numbers, right? This guy should be number, this guy should be numbers. So you can solve, from here you can solve like, let's say you can have, x minus c equal to some number in here, right? I write number in here. And then for this inequality, let's denote by, like k0, right? So basically that is x minus c less than k0 greater than negative k0. And then your x should be less than k0 plus c and greater than negative k0 plus c. Okay, so you already have some interval of x, but that's not all. That's it. That is just the first step. The second step you need to do is you need to consider the series at two endpoints. Where's that? The first endpoint is this guy, and the second endpoint is this guy. So you plug this guy and this guy into your original series. So you plug into this series, an x2 minus c to the n, m from 0 to infinity. And you have, you plug those guys in here, this into x, and then the second case, this guy into this guy. So you get two numerical series, and you have to consider the convergence of those series. And then compile with this interval, you can do, final answer. Okay, so that is, the whole problem related to the interval of convergence. This is really important, right, problem. So that's why I describe in detail. And by doing so, I think I finished my reviewing here. You can see that there are a lot of information, right? So please have a formula sheet when you study this course. Go to exam with formula sheet. That would be very nice, okay? And that help you, to solve problems. I don't require any students to memorize all those things, okay? All right, hope that the video is useful. The second part of this video is practical review. So we solve some typical problems, okay?